Using the X is small approximation to solve equilibrium problems. So, a lot of the time, the value of X you're going to end up solving for is going to be really, really small. And a lot of the time, you're going to end up with something on the denominator of your equilibrium constant expression where you're subtracting that X away from a number that is quite a bit bigger than it in terms of orders of magnitude. So often what you can do is use what in mathematics is called the X is small approximation, okay? Think of it, say you had, 100 minus X on the bottom of an equation, and then you solve for X, and X is 0.0001, and you have to give your answer to 4 sig figs. You don't even need to bother subtracting off that 0.00, however many zeros I said, 1, okay? And we can use the same kind of simplification here, which saves us from having to multiply out loads of brackets, potentially make an error, substitute into the quadratic formula, etc., etc. With one caveat is that you always need to check that x was actually small. And the way you do that is you take whatever you solve for x and then work out what it is as a percentage of the number that you subtracted it from. And if that is less than 5%, usually it's okay to ignore x. Sorry, x. So that is just when you're subtracting x off a number that is much bigger than itself in the denominator of your equilibrium constant expression. So speaking of which, I guess I should write an equilibrium constant expression for the reaction we're looking at. This is an equilibrium constant in terms of pressure, so it's a Kp. So that is going to be equal to the partial pressure of our product, which is nitrosyl chloride, NaOCl, and that will be squared because we have two of those in the stoichiometric equation, and then that will be divided by the partial pressure. I should probably do something to denote partial pressure. The partial pressure of nitrogen monoxide, so the pressure of nitrogen monoxide, that will also be squared. I'm going to have to move this somewhere where you can see it a bit better. Times the partial pressure of the other thing, chlorine. Okay, and that will be equal to, we've been given Kp, that is going to be 4 times 10 to the power of -6. All right, sounds good to me. So let's put this somewhere you can actually see it because I overestimated how much space I have. Okay. There you go. So one equilibrium constant expression in terms of pressure. So can we predict the equilibrium pressure of nitrosyl chloride using only the tools available to you? Yes, of course we can. Let's not be pessimistic about these things. So we have the initial concentration of nitrogen monoxide and the initial concentration of chlorine, and initially there is no nitrosyl chloride, so we can make that useful assumption. We don't have to go ahead and calculate reaction quotient, that the reaction is going to proceed to the right in order to reach equilibrium because we don't have any product, so we have to, go ahead and make some. So this is going to be in terms of the partial pressure of each of our reactions and products. So partial pressure of nitrogen monoxide, partial pressure of chlorine, and partial pressure of the nitrosyl chloride. Okay, so those are our reactants and products. Okay, so let's write in our initial, not concentration, partial pressures. We can take the same approach. So initially, we have 8 atmospheres of nitrogen monoxide, and we have 7.8 atmospheres of chlorine gas. This sounds like not a very nice mixture, just putting it out there. And then the nitrosyl chloride is 0. All right, so then the change row, this is when we're going to be smart and look for something with a stoichiometric coefficient of 1, which is going to be our chlorine, okay? So we're going to let the change in partial pressure of chlorine equal x. Now our reaction is going to be proceeding to the right. So reactants are going to be converted into products, which means chlorine is getting used up. So that change in the concentration, sorry, the partial pressure of chlorine is going to be minus x. All right, and then we can go forth and multiply and populate the rest of that change row based on our reaction stoichiometry. 1 mole of chlorine reacts with 2 moles of nitrogen monoxide. So for every 1 mole of chlorine that gets used up, 2 moles of nitrogen monoxide are simultaneously getting used up. So those both are going to have a minus in front of them. All right, so for every 1 mole of chlorine, we are forming 2 moles of nitrosyl chloride. So plus 2x will be the change in the nitrosyl chloride partial pressure. So then my equilibrium row, I am going to deduce by adding down each column. My initial plus change will give me my equilibrium partial pressures in terms of the unknown x. So for my partial pressure of nitrogen monoxide, that's going to be 8 minus 2x. For my partial pressure of my chlorine, that's going to be 7.8 minus x, and then for my partial pressure at equilibrium of the nitrous chloride, that will just be 2x. All right, so I've already written an equilibrium constant expression in terms of Kp, and we know what the actual value of Kp is, so now we can substitute in those equilibrium concentrations in terms of x, so that's these suckers right here. So let's put them in. So Kp equals partial pressure of nitrosyl chloride at equilibrium, so that's going to be 2x, and do not forget, from our equilibrium constant expression, that will be squared. Sort you out in a minute. And then on the bottom, we're going to have the partial pressure of nitrogen monoxide at equilibrium, so that's 8 minus 2x, and that will also be squared. My brain is already hurting, anticipating having to rearrange this algebraically. And then the partial pressure of chlorine at equilibrium is 7.8 minus x. And all that will be equal to our equilibrium constant in terms of pressure, which is 4 times 10 to the power of minus 6. Okay, so let's fix that. So I am going to go out on a limb and I am going to say, let's use the x is small approximation because I want an easy life. So the x is small approximation is saying, hey, this 8 minus 2x, if x is like really small, this minus 2x is going to be negligible. So essentially everything in this bracket is going to be x anyway. So why don't we just go ahead and ixnay on the minus 2x. Same with this 7.8 minus x. If x is 0.001 or something, then it's essentially just going to be 7.8. So suddenly that math looks a lot better, makes me happy. So what I have now is just 2x squared over 8 squared times 7.8. Which is just going to be a number, right? So let's just work out what those numbers are. Okay, so on the top here, I have simplified this to 4x squared. Let's put you here so that you look more symmetrical. So 4x squared, and then on the bottom, I just have 8 squared times 7.8. So 8 squared will be 64 times 7.8 will be 499.2. Thank you, calculator. And all of that is going to be equal to that 4.6 times 10 to the power of minus 6, which is just a number, right? So now we can see algebraically that's going to be much easier because I can multiply both sides by the 499.2, and then I can divide by 4, and then I can take the square root of whatever number I get on the right hand side to end up with x. Yay. Okay, so I'm going to scoot to up the top right here where I've got space. So 4.6 times 10 to the power of minus 6, be careful how you put that in your calculator, times 499.2. the suspense, is a small number like 0.022 blah 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 blah, and then we're going to divide that by 4 as well. So I'm going to end up with, you know what, I'll just do it for you in steps, just so you can see what we're doing here. 4x squared is equal to the 4.6 times 10 to the minus 6 times 499.2, which is 0.002296. This is more sig figs than we need, but whatevs. So then I'm going to divide both sides by 4 and take the square root to get x. So x is going to be this 632 divided by 4, and then I'm going to have to like somehow make this look pretty by drawing the square root. Let's see how good my mouse drawing skills are. Something a bit like that. So square root of all of that will give me my number. So divided by 4, take the square root, and that gives me x equals 0.02. So we've got a number. Don't be like lazy and be like, I've got a number, that's the answer. Remember what x actually is, 0.2. How many sig figs have we asked for? It's not going to be any more than 2. All right. Oh, the final answer is to one significant digit. Okay, so I've got x equals 0.024. So then what I need to do is look back at my equilibrium concentrations in terms of x, right? So I can see that I've been asked for the equilibrium pressure of nitrosyl chloride, which is 2x, okay? So the pressure of nitrosyl chloride from my equilibrium row equals 2x, so that's going to be equals 2 times 0.024, which is going to be about 0.04, okay? So 0.04 atmospheres to one significant digit, and that is my answer. But like I said, there is that one caveat that we probably do need to check, and that is, was x really small? So if we go back to where we made that assumption down here, okay, so what I need to do is, now I know what x is, I should really sort of take that x and work it out as a percentage of the number of what I've been subtracting it from, whether that really is small or not. So let's look at this 8 minus 2x. So even if we had 2x, which I've just worked out as 0.04, 0.04 divided by 8, and then multiply that by 100 to convert into a percentage. And if it's less than 5%, it's cool, it's gravy. So that is, hang on, 0.4 divided by 8. I could do this in my head. What am I doing? It's exactly 5%, so that's fine. And if I did, oh, sorry, not 0.4, 0.04. So that's half of a percent, 0.5%. So that's fine. I should check the other one as well. So the 7.8, so x was 0.02 divided by 7.8, and I'm sure you can anticipate already that is going to be definitely less than 5% of the number that it was being subtracted from. So what do you shake out to be if we're dealing with, absolute numbers? So 0.02 divided by 7.8 times 100, yeah, that's like 0.25%. Sorry, 0.025% even. 0.02 divided by 7.8 would help if I can use a calculator. So either way, we are more than good with using that x as small approximation, okay? But you do need to check, okay? Because if you didn't, if you found that the x really was significant, if it was more than 5% of the number you're subtracting it from, as a ballpark figure, then really you're going to have to go ahead and multiply that all out and solve the quadratic and have a less fun time than we just did.